Hey folks, how's it going? It's Mr. Murray, and I'm so excited to bring you this video on solving systems of linear equations using the method of substitution. So I know this has totally been a method that's really challenging, and coming off solving linear equations using graphing, those systems that is, we saw some situations where there was issues, right? One of those, for example, is when the X and the Y of your intersection point, one or the other coordinate, right, isn't a whole number. And that's challenging because on a graph, you wouldn't be able to locate it. And if you were going to do guessing and checking, it's not something that you might like naturally think of. So we said, we're going to need another method. So I know folks have been struggling with substitution potentially, and so that's why I thought I would create this video just going over substitution. And so this might be a longer video, but it's designed for people of all levels. So if you don't know where to start, you might need to watch more of the video. If you feel really confident and you want to skip ahead to the extra practice, you can do that as well. Go ahead and check out in the description some timestamps, because that will allow you to skip through the video and watch it at your own pace. All right, so I thought we get started by solving a system of linear equations by substitution using this example. So I have three teal squares plus 3 round oranges equals 45. And I also know that one of the oranges equals 2 of the teal squares. And so what I might want to know is, what is the value of one of the teal squares and what is the value of one of the orange circles? Maybe we're on some foreign planet where this is the kind of currency they're using, something like that, right? Just kind of how like a nickel is 2 nickels is equal to a dime, right? So let's see if we can figure out how to find the values. And in doing that, hopefully you see how this equation looks differently, or these equations, I should say, looks differently than what you guys saw when you were doing graphing, okay? Namely, you can see that we already know the value of the orange circle, right? We know that an orange circle is equal to 2 teal squares. And so what that means is, if you think about it, if I was to rewrite this initial equation, right, I have these teal squares, but then think about it, each one of these orange dots we know is the same thing as 2 of the teal squares. So I can take each orange dot and replace it. And that's the thing we call substitution. Now I'm allowed to do it because, right, a orange dot and 2 teal squares, you're told, are the exact same thing, right? So now what that gives us is a whole new equation. It gives us this being equal to 45. All right, and this is a game changer, because now what you can see is we only have one type of variable. And so remember, when you have one variable in your equation, that is when you're going to get one number, in this case, one number as a solution. Remember, when you have multiple letters, that's when you get one of them alone and there's letters on the other side. All right, that's for another time. So how many of these do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 of the teal squares is equal to 45 in our alien currency. So what is one of the teal squares worth? Well, you just divide by 9. And what do you get? You get that one of the teal squares has a value of 5. And now if I want to get the other one, right, well, I have this relationship right here, right? I know that one of the circles equals 2 times one of the teal squares. And now we know what a teal square is worth, right? So it's equal to 2 times 5, which is 10. And now we have a solution to our system. Given the 2 constraints, we now know that a teal square is worth 5, whereas a orange circle is worth 10. All right. And so that's the idea of substitution. You're typically going to have one of the equations where one of the letters is either already alone or you can easily get it alone. And then you're going to take like either a number or an expression and you're going to plug it in the other formula. And that plugging in is where people are going to tend to struggle, I've noticed. And so that's what we're going to focus on. All right. So if you want to see this example done again, please feel free to go back, rewind, and take another look. But what I'm going to do is I'm now going to move on to just like a general overview here about substitution. So when do you want to use substitution? And this is getting into the big skills for this chunk of the unit. Remember, skill 1 is to learn the 4 ways to solve linear systems. We talked about guessing and checking, right? You could take a guess. It could work. We talked about graphing. All right. And now we're talking about substitution, right? We got one more that is waiting in the wings. Okay. So we want to know not only how to execute them, but when we might want to use one instead of the other. In theory, because all of the methods are valid, they will all yield the same solution. But, right, we know that, for example, you might not guess and check and answer like 9 halves, 27 29ths. That could be a solution to your system. But again, it's not something that you're going to really find through guessing and checking. That's not a natural guess. So, okay, when would you use substitution? So you use substitution when either graphing seems too hard or it's likely to not be giving you whole numbers. You can see an example here. Another example would be like, imagine like 5x minus 3y equals 19. And then you have 10x minus 2y equals 13. That one right there, you would not want to do graphing, right? Getting the 5 and the 3 to balance out to a 19, right? We know, and that's kind of why I ramped up the difficulty of the levels of problems in class, is that you'll see that, yes, sometimes you can get some quick combos, graphing works, but that's not always a guaranteed thing. So in this case, I would not want to be graphing this kind of system and using that as the solution method. So that's one time you want to use it. Another time you really want to use substitution for sure. Definitely, if you encounter a case where one variable is already solved for, it's alone, or you could easily get it alone. So if you look at this example right here, you can see that y is already alone. So you can just take 5x minus 7 and you can actually substitute it for y in the other equation, as we're going to see. That's a really good time to just plug it in, get the value of x, and go, without having to say, all right, -7 up 5 over 1. I promise you, when you get really strong with doing substitution, you really pick it up, in the time it takes you to graph the first one, you would be able to solve this by substitution for sure. All right. When not to use. So I would not use this when it's hard to get one of the variables alone. So as you're going to see in the top one that we just looked at, y was already alone. But in this example down here, you can see that if I was to get y alone in the first equation, let's say, I would have to add 6 and divide by 5. Now that's going to have some really ugly fractions. And then when I put that into the other equation, it's going to really, really not look nice. So it's going to be hard to get the y alone. You know, we really sometimes struggle with isolating letters like that. So if you don't divide the 5 correctly, there's going to be errors. So that's when I would avoid using substitution. And actually what you're going to find, we're going to learn as the next idea, when you add these equations up, if you were to add these two equations to each other, the x's actually cancel because it's -6 plus 6. And then you'd get 9y because the 4y plus the 5y. And then 1 plus -10 is -9. And really quick, you can already get y equals -1 like that. So see, in the time it would have even taken you to make an XY table, you can already know that y equals -1. So another reason you really want to think about, right? And I'm not asking you to spend a lot of effort. In fact, I want you to be able to find the one to get you to the answer fastest. That's why I'm emphasizing that as a skill. So some folks have asked me, like, Mr. Moray, can you just give me the how do I do it? So I've tried to summarize the idea behind substitution as best I can in these 4 steps. 1, find the equation where it's easier to get the variable alone. So look at it and say, is there an equation where I could get x or y alone really, really quick? If you have like a coefficient of 1, so like for example, this y has a 1 in front of it. If one of them has a 1 in front of it and you don't need to divide to get the letter alone, that's a really good thing that you might want to look at. Okay, so see if that's possible. If you really cannot execute 1, you're going to find, and that's going to be like a motivation for the next strategy, you're not going to want to do this. So assuming you can, go to the easier equation, get one of the letters alone. You're going to, that's like 1 and 2. Then when you get that letter alone, you're going to take it and you're going to plug it in to the other equation. What that's going to do is now that other equation is only going to have 1 letter in it. So in this case, if I was to plug the 5x minus 7 in for y, right? So since I know that y is equal to 5x minus 7, instead of writing y, I can write 5x minus 7. So you can see that now this turns into an equation with only x in it. And that allows me to then solve it and get a number. So for example, if I was to solve this out, I would get -3x minus 10x, so it's -13x. Now -2x times -7, that's plus 14 equals -12. And then I would subtract 14 on both sides. And then I would divide by -13. And I would get x equals 2. That's step 3. Step 4, you take the number that I just got, 2, and you plug it back into the equation from step 2. Now, it doesn't actually matter which one you plug it into, because x has to be 2 for both of them, right? At that intersection point, x is going to be 2 in either case. But think about it. If you could choose the easier one or the hard one, and you're going to get the same answer either way, you know what I mean? I leave it to you as long as you get it in a valid way, right? So in this case, I would go to the top one. So 5x minus 7, 2 times 5 is 10. Right? 2 times 5 is 10. 10 minus 7 is 3. So that means the solution is 2, 3. Okay. Okay. So that's a little breakdown of the how. Let's take a look at a detailed example. Okay, so here's an example along with the steps. If you feel confident that you can execute this problem, I encourage you to pause the video, try it, and then unpause it and watch me do it and see if you got it right, if you feel confident. If not, I'm going to do this example. So the reason that this would not be one you would want to start by graphing, once you really get strong and confident in the process of substitution, is because the 7 and the 3 being the 21, that might be difficult to make a table and plot out. The x plus y being 13, you'd have to set up your x and y coordinates right. Or you might not, right? You have to set up the x and the y's. You'd have to make sure the whole graph fit on it. There's no guarantee the intersection point is even on the graph. And there's no guarantee the intersection point's a whole number. So we're going to try substitution. There are many correct ways to do this problem. I'll talk about that as I go on, but I'm going to start by getting y alone. So if you look at the bottom equation, x plus y equals 13, right? So one thing we notice is that it would be relatively straightforward to get y alone. So if I was to minus x on both sides of the equation, right, I'm allowed to subtract something from both sides. I would get y equals 13 minus x, okay? So that is telling me the value of y. And then what I could do is I can now say, well, what about the first equation? So I can take the 3, but wait a minute, instead of writing y, I know that y is equal to 13 minus x. So that means that writing y and writing 13 minus x doesn't matter because they're the same thing. But here there's an advantage because now there's only one letter in the equation. That letter is x. So again, do your waves super careful. So we have 7x. So this is minus 3 times 13. Negative 39, negative 3 times negative x, positive 3x equals 21. Okay, now the right thing you're going to want to do is a good practice is to combine like terms. So I see I have a 7x and a 3x. I'm going to write that as 10x minus 39 equals 21. And I know there's an inclination to like skip work. I sometimes, honestly, I do it in class sometimes. It really is important to show all your work though, because when you make a mistake, you're going to want to be able to figure out where it happened. All right, now I'm going to add 39 on both sides. Be a good role model here. 10x equals 60. So that means x is equal to 6. And so then if x is equal to 6, what I need to do is I need to come over here. And I know that, well, if x is equal to 6, y is equal to 13 minus 6, because x is equal to 6. And that is 7. Okay. So if I was going to check this, how would I do it? I would take x, I would plug it in. So that would give me 6 times 7, 42, minus 3 times 7, which is 21. 42 minus 21 is 21. And 6 plus 7 is 13. So that confirms a final answer of this question. You could write it as 6, 7, or x is 6, y is 7. Okay. Please make sure you understand how I did this. And I'm now going to move on to the next one. All right, moving on down. And again, feel free to pause, rewind, go back, anything you want. It's all about doing it at your own pace. So I'm going to do this one a little bit faster, okay, than the last one. All right, so here we go. So I'm going to find out which one I want to get alone. And of course, this previous one, you could have gotten x alone instead of y alone, right? It wouldn't have mattered if you had gone back and you had isolated x instead of isolating y. I chose y. All right, so here we go. We got 4x plus y is 13 and 2x plus 5y is 20. So I noticed that on the bottom, it would be one step to get y alone. All right, this would be very difficult to graph, right? But if I was to minus 4x on each side of the bottom, I would get y equals 13 minus 4x. Or you could also say y equals negative 4x plus 13. All right, now up top, here's what we have. If that's true, then let's see what we got. 2x plus 5. And now, instead of writing y, I'm going to write 13 minus 4x, okay, equal to 20. Okay, now I'm going to distribute. So 2x plus 65 minus 20x equals 20. So I have 65 minus 18x equals 20. Just combining the like terms, the 2x minus the 20x. So I get minus 18x. I believe negative 45. This is turning into an interesting one. So I have x equals negative 45 over negative 18. Okay, it seems like a weird fraction, but that's okay. 45 over 18, we should try to simplify. It turns out that 9 goes into each one. So 9 times 5 is 45. 9 times 2 is 18. If you did it in a calculator, what you'd find is that the calculator would tell you 2.5. And I would completely accept 2.5 as an answer. Okay, so now to get y, what we're going to do is we're going to go back to our original equation. We're going to go y equals 13 minus 4. And now that we know what x is, it's 2.5. We can plug in that 2.5. Okay, so 2.5 times 4 is 10, meaning y is equal to 3. So let's check our work. So if we go back to the original equation, 2.5 times 2 is 5. 5 times 3 is 15. 5 plus 15 is 20. So the first equation checks out. And then if we do 2.5, 2.5 times 4 is 10. And 10 plus 3 is 13. So that means both equations are true, which confirms that our solution is 2.5, 3, or x equals 2.5, y equals 3, okay? That is what we got. Hopefully this example made sense. Again, our steps are to look for the equation where it's easier to get the variable alone. So the bottom one, it was easier to get y alone. Then we got y alone, step 2, y equals 13 minus 4x. Then step 3, we took that 13 minus 4x, we substituted it in for y in the other equation. That allowed us to get x alone and get a solution for x of 2.5, that's step 3. And then step 4, we plugged back in to the original equation, y equals negative 4x plus 13, or 13 minus 4x, however you wrote it. And that gave us our equation for y. Of course, right, we also did that unofficial 5th step of checking our work. All right, so feel free to, again, rewind and pause, use this video for what you need it for. I'm going to go ahead and look at this question from the lesson. I believe it is the one on substitution. So I believe lesson 13, practice problems. So 2 different examples of solving systems of equations with substitution. One where a variable is already alone, x equals 4, and it's a number, and one where a variable is already alone and it's an expression. So in this first one, because I know that x is already equal to 4, I would just take 4 and plug it in for x in the first equation, because you're already told x is equal to 4. So 2 times 4 is 8. Okay, then you minus 8 on both sides. Negative 4y equals 12. And then you divide both sides by 4. Y equals negative 3. So you get, as your solution, 4, negative 3. Makes the bottom true because the x is 4. Makes the top true because you get 8 plus 12, which is 20. That's type 1. You're not likely to see that because, right, that's just like plug it in and get the other one, but I guess it's possible. All right, this next one down here, what you're going to do is you're going to be working with a whole expression. So we're going to write 2x minus 3. And then instead of writing the y, we know that y is equal to 6x plus 11. So instead of writing y, we're going to open our parentheses and we're going to write 6x plus 11. Ooh. And this is all going to be equal, once I get my pen back, all going to be equal to 7. All right, and then what we got to just work on a little bit is, and no worries, we got to work on our distribution. So 2x minus, so minus 3 times 6 minus 18x, negative 3 times 11, because you're subtracting 3 times 6x, and then you're subtracting 3 times 11. So you're subtracting 18x, and then you're subtracting 33. I recommend when you have a negative in front of the number that's being distributed, you like circle them and group them up. I think that'll make things easier for you. Hopefully that helps. Okay, now I'm going to combine like terms. These are my like terms. Negative 16x minus 33 equals 7. Now I'm going to add 33 on both sides. Negative 16x equals 40. And then finally, I'm going to divide by negative 16. So I get x equals, so if I divide by 4, I get 10 over negative 4. If I divide this by 2, I get 5 over negative 2. So I believe negative 2.5. Okay, if x is negative 2.5, then I can use the top equation to find y. Can you use either one? Sure. In fact, I'm actually going to use the bottom. So 2 times negative 2.5 minus 3y equals 7. Again, I can do that because I know x is negative 2.5. So this is negative 5 minus 3y equals 7. To get this negative 5 to cancel out, I'm going to have to plus 5. And do that on the right. So negative 3y equals 12. So y equals negative 4. Okay, if you plug it on the other one, you get negative 2.5 times 6. So that would be negative 15 plus 11, which is also negative 4. So your final answer would be negative 2.5, negative 4. Folks, please make sure you understand how I did that and understand what the solution is, as well as the method for finding it. And then I am going to move on to a couple more examples. All right, so here's some examples from a worksheet here where we're going to be solving using substitution. So you can see that this is actually very similar to the one you have there. So I'm not going to actually do that one because we've kind of already done this one. All right, now I'm going to go ahead and show you this next one right here. So here we go. 2x minus 3y equals negative 1. Y equals x minus 1. So what we know is y is already alone. So 2x minus 3, and instead of writing the y, right, I'm going to write x minus 1 equals negative 1. Please make sure you understand how I did that one, okay? Took the x minus 1 and I plugged it in for y. Okay, now I'm going to do 2x minus 3x. Now the negative times the negative plus 3 equals negative 1. Then 2x minus 3x equals negative x. So negative x, and then I'm going to minus 3. Negative x equals negative 4. And in that case, since negative x equals negative 4, positive x equals positive 4. So that means x equals 4. And now if y equals x minus 1, well, what's 4 minus 1? That is 3. Let's check our work. X equals 4 on the top. That would give me 8. Y equals 3. 3 times 3 is 9. 8 minus 9. Yep, that's negative 1. And 4 minus 1 is 3. So that checks out. 4, 3. Or as a point like this. Okay. So we see a similar thing with number 3. So number 3, what we have is 5x minus 4. And then instead of writing this one, y, I'm going to write negative 3x plus 5 equals negative 3. Now I'm going to distribute 5x plus 12x minus 20 equals negative 3. Make sure you can see why the negative times the negative, giving me a positive. So 17x. So we combine like terms. You can use a calculator to help you combine like terms. You can just add or subtract the numbers that are in front of the letters. Okay, then I'm going to add 20. So 17x equals 17. So x equals 1. Again, you can imagine how tough it would be to plot the function on the bottom or the line on the bottom. That'd be really hard to actually get out there. You could actually probably solve the system in the time it would take you to make a table and a graph of the bottom one. So if x equals 1, y equals negative 3 times 1 plus 5. So negative 3 times 1 is negative 3 plus 5, which is 2. Okay, so y is 2. Does that work? Let's check the bottom. So if y is 2, we get 5 minus 8, which is negative 3. And if y is 2, we get, and x is 1, we get negative 3 plus 5, which is 2. So both equations check out. All right, so that's a little example of how we do a couple of these. I'm going to move on to a couple more examples that are just a little bit different, okay? And here you can see that the variable is not alone. So I'm going to do 2 more examples, and then that'll wrap things up. I'm going to do number 8 and number 9. Okay, so number 8, we want to get one of the letters alone, okay? So I'm going to go to the bottom because see how I see that x has a 1 in front of it? This means that it's going to be easier to get that one alone. So what I'm going to do is I'm going to add 2y on both sides. And that's going to give me x equals 11 plus 2y. And now that I know that, I'm going to come up top and I'm going to do negative 7, 11 plus 2y minus 2y equals negative 13. Okay, I can make that substitution. And now I'm going to distribute negative 77 minus 14y minus 2 more y equals negative 13. So combining like terms, negative 77 minus 16y equals negative 13. Okay, so I'll add 77, something you could do with a calculator. Negative 16y equals 4. Y equals negative 4. Okay, and if y equals negative 4, then we come back here, x equals 11 plus 2 times negative 4, which means 11 minus 8, which means 3. So if I, again, check that out, 3 minus negative 8 is 3 plus 8, which is 11. Up top, I'm gonna make sure I know x is equal to 3. Up top, negative 21 plus 8 is negative 13. So x equals 3, y equals negative 4, or 3 negative 4. Okay. All right, on the bottom one last example, we can see that up top, y is almost alone. So the thing that you get alone could be in the top equation or the bottom equation, okay? And remember, you could write this or you could write -2 plus 5x. Lots of ways to do this right. Then I'm going to come to the second equation, -3x plus 6 times 5x minus 2 equals -12. So I distribute and I get -3x plus 30x minus 12 equals -12. So I combine like terms, 27x minus 12 equals -12. This is going to be a tricky one. I can feel it. X equals, 0. 27x equals 0. So could x possibly equal 0? Yeah, it could. Because if x equals 0, then if I plug 0 back in, we get y equals -2. Does that work? 0, -2. 6 times -2 is -12. There we go. 0, -2. So again, folks, hopefully you found this video on substitution to be helpful, and hopefully it highlights one of the methods that you folks can use to solve systems. Is it always the most efficient method? No, it's not always the most efficient method. It's challenging to learn it first, but hopefully we'll continue to kind of like make some strides towards it. All right. Keep the questions coming, folks. Keep working at it. We're going to get there. Thank you so much for watching. Don't forget to love math. And remember, no matter what, you can do it. All right. Don't forget that. Thanks again, folks. Have a wonderful day. And don't forget to love math.